For this section, we're going to study an important type of limit from calculus, and that's the limit of a difference quotient. But before we get to that, we got to first learn about these things called tangent lines. So, calculus is a branch of mathematics that studies the rates of change of functions. If you go on to take a course in calculus, so like say, for example, if your freshman year of college, if you haven't taken AP Calc, you're probably going to, well, there's a good chance you'll have to take a calculus class. You'll learn that rates of change have many applications in life. Earlier in this text, you learned how the slope of a line indicates the rate at which a line or rises or falls. For a line, this rate, also known as the slope, is the same at every point on that line. Now, if we have something that's not a line, the rate of the change or the rate of the graph rises or falls changes from point to point. So here's some examples of tangent lines. So, a tangent line really, it just means it touches one part of the graph. So like this one touches right there at point P, but the other parts of that line tangent to that curve don't touch. It's just like it just barely grazes that point or that point there. Same thing here. It's running tangent to that line. It just barely touches it. It's not really going through that part of the line. And same thing down here in this parabola. It touches that point and just kind of only touches that point. Doesn't cross anywhere else. So, talk more about the slope of the graph. Because a tangent line approximates the slope of the graph at a point, the problem of finding the slope of the point or the slope of a graph at a point is the same as finding the slope of the tangent line at that point. So this example down here, we're asked to use this figure to approximate the slope of the graph of f of x equals x squared at the point 1, 1. Now I've already taken the liberty of putting in some other information in there. So we're going to say the slope at point 1, 1. What we're going to do, we're going to use the slope equation. M equals delta y over delta x. We don't have like specific coordinates you can plug in. I mean, if you wanted to, it'd be y2 minus y1 over x2 minus x1. But honestly, right here, we already have our y change in y2 over our change in x1. So our slope in this case is just going to be 2. So, nothing too sophisticated so far. Now, in that example, we approximated the slope of the graph at a point by creating a graph and then kind of eyeballing the tangent line. A more precise method of approximating tangent lines is to actually make use of this thing called a secant line through the point of tangency and a second point on the graph. So, say for example, if we're trying to calculate the slope at that point, we're going to approximate it using the slope from that point to that point, but then kind of change as we go along. So the beauty of this procedure is that you obtain more and more accurate approximations of the slope of the tangent line by choosing points closer and closer and closer to that point of tangency. So again, if we're kind of focusing on this point, kind of the bottom left here, we're going to get slopes of different points. So like these 2 points are decently close together, but then we're going to get the slope of points that are even closer, then the slopes of points that are even closer, and we get closer and closer and closer, so much so that essentially the points overlap, and that's how we get the official tangent line. So we say, as h approaches 0, the secant line approaches the tangent line. Now we're talking about h approaching 0. That's really getting into what we've been talking about for limits. So let's use that in terms of limits. So using the limit process, you can find the exact slope of a tangent line at x and then f of x, the output. Using this definition, the slope m of the graph of f at a point x comma h, or f of x, so x and y coordinates at that point, is equal to the slope of the tangent line at that point and is given by the limit as h approaches 0 of m sub secant, so that's the slope of the secant line, and we're going to say h approaches 0, or limit as h approaches 0 of f of x plus h, so kind of a point a little bit to the right, minus the output over h. And again, this is essentially delta y over delta x. And this is also assuming that the limit exists. So from this definition above, you can see that the difference quotient is used frequently in calculus. And using the difference quotient to find the slope of a tangent line to a graph is a major concept in calculus. Folks, let's try an example of this out. So, next page, we're asked to find the slope of the graph f of x equals x squared at the point -2, 4 using a difference quotient. So the difference quotient, we're going to say the limit as x, sorry, not x, but h approaches 0 of f of x plus h minus f of x, and I'm actually going to color code this, and let's make f of x blue in this case, over h. Now, we're doing this function f of x equals x squared. So f of x plus h is actually going to be, instead of x squared, it's going to be x plus h squared minus the f of x, well, that's just normal x squared. And we're going to divide that by h. Right now, we just have a lot of symbols here. Now, what we can do is we actually can start plugging in our x values. So we're going to plug in the x value of -2. So in the first part, it's going to be -2 plus h squared, and then minus that -2 squared, still over h. We still don't know what h is. Now, the -2 plus h squared, remember, when you have some binomial squared, or really any group squared, it's going to be that group, -2 plus h, times -2 plus h. We'll go through and distribute that in a minute. The other one, minus -2 squared is +4. Well, we probably could have figured that out based off of that was already given to us. This whole thing still divided by h. What we're going to do here is we're going to distribute, and I'm going to start combining things now. So we're going to distribute the -2 to the -2, giving us a +4. So we got 4. -2 times h gives us -2h. h times -2 over here is -2h again, and then h times h is plus h squared, and we still have that -4. Let me actually change the color of this to match up with the red that we were just working with. Okay, and then we still have that -4 that we had previously. All that still being divided by h. Now looking at this, we can start slashing. We have a 4 and a -4, so those are going to go away. We also have -2h minus 2h, that's going to give us -4h, and then we still have the plus h squared, all this being divided by h. Now I'm going to rearrange this to make it h squared minus 4h over h. And from here, what we can do is, in that numerator, we can factor out an h. It's going to be h times, oops, sorry, why is that being fussy? H minus 4, factoring out an h from each of those. And now we can cross off one of the h's. So it's going to be just h minus 4. Now I left a lot of space over here. So we're going to use this, and we're going to say the limit as h approaches 0. Sorry, getting ahead of myself. So using that h minus 4, now what we can do is we can plug in h equals 0. So when we plug in h equals 0, we got 0 minus 4, which gives us -4. So the slope at the point -2, 4 is -4. We'll look at that graphically in just a minute. Alright, so I'm going to use Desmos. I'm going to use that x squared graph, and this is what x squared looks like. Now you see at x equals -2, we're up at that 0.4. That is something we already knew, so, well, I can't. There we go, -2, -4. Now I've already taken the liberty of coming up with an equation that has a slope of -4. You'll see right there, it's got that slope of -4, and it should touch that point right there. So if I graph that, you'll see this graph, and I'm going to zoom in a lot on it. It's going to touch that point and not quite cross that line. You can see I'm getting really, really close to that point. So that point -2, -4. And it touches it, but doesn't quite go through the red line. Now it's hard to see because they're so close right now, it looks like they overlap. But it touches that point and just kind of hovers on the outside. That blue line is always on the outside of that parabola.